Okay. Hi everyone. My name is Selcuk Sandikci. I'm an embedded AI architect at NXP, and today I will talk about model and AI inference optimization for edge devices that we have at NXP. A very brief slide about NXP. It's a rather big company, global one, creating semiconductor chips basically, publicly listed as well, and there are basically, I would say, 3-4 important things that defines NXP, which is the safety, security, connectivity, and also intelligence at the edge. The company is quite active in automotive, industrial IoT, mobile, and communications. Let me go through here fast. Basically, there are countless of applications at NXP regarding AI ML. For instance, for automotive, ADAS, safe driving is an important domain of applications there. Lots of EV battery health monitoring, estimation, and so on. When it comes to industrial automation, we are now currently working on agentic AI systems so that there could be autonomous decisions made at the edge. Regarding smart home, building, and city, we have, for example, conversational AI software pipelines, we have generative AI, service drones, home patient, elder monitor, and so on. And finally, there is a, let's say, product line, business line, which is very much focusing on patient monitoring, for example, blood pressure monitoring, and so on. Okay, then I thought this slide was useless or kind of irrelevant for this audience, but then when I was chatting in the lunch, I noticed that not everyone knows the edge AI. So as far as we are concerned, edge AI is deployment and the inference of the AI models on the local edge devices, such as like MCUs or processors, where these devices are close to the data collection place. And instead of doing this on the cloud, if you do it like that, then what are we gaining? Basically, we can do real-time decision making. We don't need to send the data to cloud, right? We have reduced latency. Again, we don't need to send to cloud. They are always almost low power consumption. Data stays on the device, so there is a privacy benefits, of course. And you don't need connectivity most of the time. So this is the typical pipeline, very simplified, of course. So the model training happens in a cloud setup or a cloud-grade hardware setup with a dataset and model. And this is where typically most people operate. Then we need to go through a certain model optimization conversion step that I will talk a lot here in this talk. Then we will have our optimized model. Then we will need to deploy it on our edge AI hardware using this hardware software environment. So the previous talk was actually doing this. So that was very helpful overall. And so we need to optimize the model quite a bit, also the inference part, to make efficient and effective deployment. So what we mean by optimizing is we want to reduce the model size or the latency of the model or energy consumption and so on. So also the previous speaker described this very nicely. Thanks for that. So the quantization, typically a must-have. You always need to do that. Then we have sparsification techniques such as model pruning that I will talk in this talk a bit. Also token pruning. So this is a lot more applied to transformer kind of models that you can do, token pruning at inference time. Lowering compression, also knowledge distillation, so that you can create smaller models. Neural architecture search, if you have the bandwidth and the compute cost for that. And final speculative decoding, which can happen or happens during the inference time, basically. I'm going to talk about the model pruning and speculative decoding. At least I'll show some of our work. So model pruning. You already have seen it from the previous talk, but okay. So model pruning, what is that? So we are going to remove some model parameters, basically to reduce computational complexity. So we do less compute. And also we have less memory requirements. And why we can do this? Most of the models are quite redundant. We have a lot of weights that you can remove them, and then you can still, keep the accuracy at a good level. This is a very simple, actually, plot from some paper, but you can see they could like compress the model quite a bit. Also, the previous speaker did that. So how do we do that? Typically, we start from a pre-trained model, then we remove weights, and then we fine-tune, and so on. But then when you are doing that, you have to select certain things, such as what kind of, I'm sorry? Okay, yes, okay, yes. Yeah. So basically, you need to define a certain criteria, like are you going to look at the weight magnitudes, or are you going to look at the gradients of the magnitudes, or how are you going to prune? Is it going to be unstructured like this? For example, here the white ones are pruned, that means they are 0. These ones are just left alone. So there is no structure to the pruning. Or you could do structured pruning, so you remove whole layers or whole channels, or semi-structured is somewhere in between. And you can do this. Oops, something is happening here. I think I'm touching the touchpad. So we could do also global and local. And well, this depends actually which method you select. For example, here we have different, pruning granularities, right? We have the structured, unstructured pruning, semi-structured, and structured. But typically they have certain, let's say, criteria on which one you should choose. So unstructured is quite flexible. It can keep the accuracy quite well. But then you will only, get some benefit from the model size. And you will always need to, have a certain hardware. Like your hardware needs to support sparse execution, or it has to have like the compression engine, or zero skipping, something like that. So that is somewhat inefficient in hardware. Semi-structured is somewhere in between, so accuracy is mid-level. You will gain from model size, latency, and again, you will need to have some sparse neural network kernels and so on. And structure is like, it's much more harsh on the accuracy size, but then you will have no restrictions when it comes to hardware, because basically you are just creating another model where it will run on the hardware with no problem. So these are quite obfuscated results, to be honest, on some of our hardware. So here we just say Edge MPU A, Edge MPU B, but these are actually real products from XP. And then we also show the latency in a normalized way. That means this is our baseline, and then this is the accuracy. This is a vision transformer model on ImageNet. And basically, we can make this model like 50% faster by applying this structured pruning, after quantization, of course, with a little degradation in accuracy, about only 3%. And on the right-hand side, we have the DeepLab V3. It's an image segmentation model. The same story applies there. Basically, we can make the model like 30% faster on the hardware. So it's actually quite effective, at least the structured pruning here. Then let me move to a different part, speculative decoding for small language models at the edge. I think like 2-3 years ago, this was a bit of a extreme, I would say. Like nobody was really thinking about running billion, parameter models on the edge. But nowadays, everyone is doing that, and so we are. So before going into the Before going into detail, let me describe the speculative decoding in a nutshell. So this is created by Google, I think about 4 years ago. So if you know about how LLMs work, you have this big model. It's going to create response token by token. And then the idea is we can have a little small model here, or a system. It will create multiple draft tokens for us in a quick way. Then we are going to give all those draft tokens to the target LLM, this one. And it's going to verify all draft tokens in one go. So this is roughly how it works. So you see this is just generating token by token. And here the draft is creating these yellow tokens, let's say, and the target is verifying. Red means it just rejects. Green means it accepts. So this is the basic idea. And then when we look at this, the literature is quite rich, I would say. But they're all meant for big models, like 7 billion and more, and like 70 billion, 400 billion, and so on. But actually, these models are really big for edge, at least most of the devices. So when we look at this regime, like 1 million, 3 billion parameter, that's actually somewhat the smallest models that you can run in a reasonable accuracy. So that's where we are interested in, and there is really not much method there. So what we did is we explored lots of different methods here. I think I'm short on time, right? Yes, I will take 30 minutes.
2 minutes, 2 more minutes.
Oh, really? Okay. Okay, so basically we explored different kind of speculative decoding algorithms here, like independent drafting, self-drafting, retrieval-based drafting, and so on. So here, these are almost like drop-in replacements. You can just apply them easily. It's challenging though for small language models. These are more sophisticated methods where it requires architectural changes, fine-tuning, and so on. And these are not even ML-based, but more like retrieval-based. So you use a retrieval-based system to draft tokens. So they tend to be quite cheap. And then we applied them on this kind of models, like 1 to 2 billion parameter range. We used this SpecBench dataset. We looked at speedup ratio and mean acceptance tokens. So these are two things which are the most important. But we all did these experiments on NVIDIA hardware. So let me briefly show you the results here. So something was striking here. So all these methods are actually reported to be very good on 7 billion parameter range, but they really don't work. They don't work that well for small language models. For example, even sometimes you have slowdowns, like 1 means your baseline, and if you are below 1 means you are actually slowing down. So it's against what you are trying to do. And then most of them didn't bring much, like 10% increase, I don't know, 15%, and so on. Then we have Eagle. That is a method which is fine-tuning based. It actually delivered all the time really decent performance. And then we have this PLD, so-called extremely cheap method, retrieval based, and it was also delivering us, good amount of, what's going on? Reliable speedups, basically. So yeah, long story short, what we see in the big parameter or big model range, we don't see it in the small model range. Actually, okay, I'll pass this quickly. It really boils down to the trade-off between the drafting time, like how much time your draft is spending to create these things, and then the quality of the draft. So if you are here, this is the best place. For example, this one is slow, right? Because it's spending a lot of time on the drafting. That's why it's slower. And Eagle is, for example, very high quality draft. That's why we gain a good amount of speed up there. So let me get to the conclusions. So overall, to run these models on the edge, especially more state-of-the-art SLMs and so on and so forth, be it model optimization, also inference optimization. Some methods work well on the edge, like for example pruning and so on. Some of them don't translate that well to the, for example, edge. So here, basically, what we do at LXP is we apply applied research. We look for methods out there. We try them on our hardware, and eventually, basically, we report them if they work well. So yeah, this is the end of my talk. Yes. Yeah, too much content.
So we have time for one question.
Yeah, go ahead.
Yeah, if there's not something else.
Maybe one.
When you compare the trade-offs of different tuning techniques,
Yeah.
I noticed that you considered that unstructured tuning doesn't improve latency. I was wondering, what are your thoughts on that?
Yeah, this one, right? So it can improve latency, but if your hardware has certain capability for that. So typically, if you have unstructured, that means you will have just random zeros, right, in your weight tensors. So then you can compress them using some compression algorithm like half encoding or Rice column and so on and so forth, right? But then you can basically make the model smaller. So when you are, let's say, sending your model to your accelerator, then you will, gain quite some time from that, data transfer or weight transfer. But then you need to decompress that model so that you could run on your hardware. So we have certain piece of hardware which can do that. So indeed, it helps. But if you really want to have genuine or like natural latency, then your hardware needs to support this so-called zero skipping. So when the weight is 0, or if the activation is 0, then it can just skip the computation. But that is always a trade-off between parallelism and the zero skipping. So yeah, it's 50 minutes talk, so we can't describe lots of things, unfortunately. Yeah.
Hank, if you have very quick question, maybe.
No, maybe continue with this. So you have pruning and quantization. So there is a phase ordering problem here. What do you first?
Oh, we always do pruning first, all the time. That's yeah, always. Yes.
And you did not read the paper from Qualcomm in Amsterdam, because they have strong remarks about that you should do first do quantization.
Then pruning.
Yeah.
Oh, okay, maybe. I know they have a paper on like quantization versus pruning, and then it was really, saying quantization is better and so on.
Yeah, it looked quite strong to me, but you can have a look. But why do you do pruning first then?
Because that's the place where you can really recover the accuracy back. If you, for example, apply pruning and then if the accuracy dips significantly, then we are going to do some fine tuning for the prune model, so we recover the accuracy. And then typically we will apply some PTQ kind of method for quantization. Then we will have the quantized model. We can combine them all, right? Like we can do a pruning and quantization, a training and so on and so forth. So they all exist. But in a practical setting, it's typically this order.
Let's discuss it offline.
Yeah, sure.